So we're going to talk about holes today with rational functions. The first thing we should always do is factor the top and bottom of the rational function, because we'll have to do this anyways when we're doing our asymptotes and intercepts. So let's start by looking at this example. If we have x cubed minus 2x squared over x minus 2, and x squared would be the GCF of the top, so I could factor out an x squared. That leaves me with an x subtract 2, and there's still that x minus 2 on the bottom. Now this is a question where there is a hole. And a hole occurs wherever there's a common factor in the numerator and denominator. So when I'm looking at this, I see that x minus 2 is the same on the top and the bottom. So this is where the hole is going to be. But the hole is always located where that factor equals 0. So the hole, we set the common factor equal to 0. So here I'll set x minus 2 equal to 0, which means there's going to be a hole at x equals 2. Now here's why a hole actually makes your graph easier. When I have something the same on top and bottom, they divide out because it's the same on top and bottom. So when I divide out that x minus 2, all I'm left with is x squared. Now you guys know what x squared looks like. X squared is just a parabola. This parabola though, again, the parabola that I'm left with is not even rational anymore. It's not even a fraction function anymore. It's just a parabola. But there is a hole in it at x equals 2. So if you look, there would actually be a little circle that represents a hole where your x value is 2. So I'd like just to turn your attention then to this. This is just an example on page 449 of your text, but you can just look up here. This is match the graphs and equations for rational functions. So when I'm looking at these graphs, I see a few things. I see that this one here has a hole in it, and the hole is located at minus 2. So that means that one of these graphs is going to have the same factor on top and bottom when I factor it. So I'm just going to quickly factor all of these. The bottom here is a difference of squares, so it's x minus 2 and x plus 2. This one I would divide a 2 out of the top. I'm left with x plus 2. And the bottom is not factorable because x squared plus 1 is not a difference of squares because it's a plus in the middle. So that one's not factorable. This one I would divide out an x and have x plus 2. And on the bottom I have x minus 2 and x plus 2. So when I'm looking at these factors, first of all I'm going to see if any have a hole in it by comparing if any factor is the same on top and bottom. So here in graph A, we're going to have the hole at x plus 2, which means that minus 2 is where the hole is located because we set the hole equal to 0. Now I want you to look at the rest of this function. This function I'm left with then is x over x minus 2. So now I see that I have all my other information comes from the graph left over once the hole has been removed. So when I look at this, I see that I have a vertical asymptote at 2. I see that I have a horizontal asymptote at 1. The y-intercept would be 0, and the x-intercept would be 0 as well. So if I look at that, all of my other information comes from the graph that's left over after the hole has been divided out. Now if I look at my graph C here, I see that there's 2 vertical asymptotes. So that's going to match with graph 1 because there's 2 vertical asymptotes there, which would mean graph B matches with 3. Also notice that there's no vertical asymptotes in this graph because it was not factorable. So that's why graph 3 has no vertical asymptotes because it does not have a denominator that can equal 0. So we're going to take a few minutes and try some of these. These are on page 452, number 2, 5, 6, and 7. And when you're finished, you can keep working on the graphs from before.